like maybe just one single atom thick. But get this, it's stronger than steel, conducts electricity better than copper, and it could totally change, everything. Your phone, how we treat cancer. It sounds like science fiction, but it's real. Today, we're doing a deep dive into exactly that. Two-dimensional materials, or 2D materials. So in this deep dive, we're going to unpack what these 2D materials actually are, why being so incredibly thin matters so much, how do they even make these things that seem kind of impossible, and we'll look at the sheer variety, this huge zoo of materials out there. Then, yeah, the really exciting part, what they promise for the future. We're talking faster electronics, new medical breakthroughs, all sorts of things. Our sources for this, they really cover the whole spectrum, the basic science right up to the latest applications.
Yeah, and it's really important to get your head around the scale here, because honestly, this whole field was something scientists thought was, well, thermodynamically impossible. The thinking was you just couldn't have stable, freestanding materials only one atom thick. But here we are. It's genuinely revolutionizing material science. So our mission today is basically to pull out the key stuff for you, give you a clear handle on this really complex, fast-moving area without getting lost in the weeds.
That thermodynamically impossible thing really jumps out. I mean, wow. So, okay, how do we even start defining these things that everyone thought couldn't exist? What are they, fundamentally?
Right. So at their core, they're crystalline solids, like ordered atoms. But the unique thing is they are literally just a single layer, or maybe a few layers, of atoms thick. Think about it like this. Sideways, they can stretch out quite a bit, micrometers, maybe more. But their height, that's squashed down to the nanoscale, often less than 1 nanometer. And that extreme thinness, that confinement to just 2 dimensions, that's where the name comes from. And more importantly, that's where all their amazing properties come from.
Okay, so it's not just about being small. It's tied to how their parent crystals are built, right? The original 3D stuff.
Exactly. They come from these layered materials where the bonds inside each layer are super strong covalent bonds, usually. But the connections between the layers, they're incredibly weak, just held together by these things called van der Waals forces. Much weaker.
Ah, okay.
And that difference is key. It lets us basically peel them apart, exfoliate single atomic sheets. That's exactly how graphene was first isolated from graphite, pencil lead. And that discovery just blew the field wide open.
So it's not just thinning something down like you might think. It's like you're changing the fundamental rules for how that material works. This dimensional shift, you called it. Quantum confinement. That means it's not just smaller, it's unlocking totally new physics. What's the biggest aha moment from that quantum effect?
Yeah, the core idea is that when you trap electrons in these incredibly thin planes, their whole world changes. Their allowed energy levels, how they move, how they behave, it's all profoundly altered. And this leads to totally new electronic and optical properties that you just don't see in the bulk 3D version of the material. Imagine taking a material that's normally terrible at emitting light, an indirect bandgap semiconductor, and just by making it super thin, you turn it into something great for LEDs or lasers, a direct bandgap semiconductor.
Yeah.
That's the power of quantum confinement. It's like we get to tweak nature's rules at the atomic level.
Wow. Okay, that's a huge transformation, just from thickness. And you mentioned every atom is basically a surface atom then. Does that mean they have this massive surface area to volume ratio? What does that do?
You nailed it. That's absolutely critical. It means you have a huge number of atoms ready to interact with whatever's around them. This super high surface accessibility is why they're so exciting for things like catalysis, speeding up chemical reactions, or for chemical sensors, biological sensors, energy storage, anything where surface interactions are the name of the game.
Got it. And these unique properties, that's why it's not just about graphene anymore, right? There's this massive diverse zoo of materials now.
Yeah.
Our sources really emphasize that, graphene kicked things off, but now we think there are hundreds of stable single-layer materials, and they cover, the whole range of electronic types.
Oh, absolutely. The variety is stunning. You've got semi-metals, like graphene itself. It has this unique electronic structure. Zero band gap, where electrons act almost like they have no mass. We call them massless Dirac fermions, which basically means they can zip through graphene incredibly fast. Perfect for, say, ultra-fast electronics. Then you have the semiconductors. Arguably, these are the most important technologically. Things like transition metal dichalcogenides, TMDs for short, like molybdenum disulfide, or even single layers of elements, like phosphorine. These have tunable band gaps, which is exactly what you need for making transistors, the building blocks of computer chips, and for optoelectronics, like light sensors and emitters.
Okay, so we've got conductors or semi-metals and semiconductors in this 2D zoo. Are there insulators too? What do they do in this flat land?
Definitely need insulators. There's hexagonal boron nitride, or HBN. People often call it white graphene because it has a similar structure, but it's a great electrical insulator. It might not sound as exciting, but it's incredibly important. It acts as an atomically smooth, insulating surface to put other 2D materials on top of. It protects their properties.
Ah, like a perfect little platform.
Exactly. And then, to round things out, you've got true metals. The ambacene family, these are 2D transition metal carbides. And nitrides, they conduct electricity like a metal, filling another crucial gap. And beyond just electronics, these materials are mechanically amazing. Graphene, as you said, is like 200 times stronger than steel, and thermally. Graphene and HBN are some of the best heat conductors known. Great for managing heat in devices.
It's just wild, isn't it? Something that thin being so strong and conducting heat so well. Okay, so moving on. How do we actually make these things? Our sources talk about top-down, starting big and going small, and bottom-up, building atom by atom. And there's this...
Right. The classic example of top-down is mechanical exfoliation, the famous Scotch tape technique used for graphene. You literally use sticky tape to peel layers off a bulk crystal. It gives you the absolute best quality, most pristine 2D crystals. Very few defects. Perfect for lab research, finding out the basic properties. But it's totally unscalable, it's fiddly, takes a lot of work, and you only get tiny random flakes. Brilliant science, but definitely not for mass production.
Okay, yeah. I'm not going to make phones that way. So for scaling up, people look at things like liquid phase exfoliation, LPE, breaking them down in liquids.
Exactly. LPE is much better for scale, and it's cheaper. You basically blast the bulk material apart in a liquid, maybe using ultrasound or high-speed mixing. Good for making large amounts for things like inks or mixing into plastics, composites. The historical issue was always, well, quality and how much you actually get. The process can damage the flakes, make them small, and they can clump back together. But there have been some really smart improvements lately. Things like doing it at very cold temperatures or using intermediate chemicals to help it along. These are boosting the yields significantly, sometimes getting like 2/3 of the material exfoliated, which makes it much more practical.
Okay, improvements there. Now, on the other side, building up bottom-up, atom by atom, chemical vapor deposition, CVD, seems like the main contender for making bigger sheets.
CVD is definitely the most promising for industry, yeah. You float precursor gases over a hot surface, often a metal foil like copper, and they react and deposit a continuous 2D film. You can produce high-quality films, even wafer-scale ones, which is what you need for electronics. The challenges are really controlling things precisely, getting exactly one layer, making the crystal domains large, keeping defects down. Plus, it needs high temperatures and vacuum systems, so it's pretty expensive.
And some materials need their own special recipe, right? You mentioned M-zenes earlier.
Absolutely. M-zenes are a great example. They're made by a unique top-down chemical process. You start with a specific 3D ceramic called a max phase. Then you use chemicals, usually strong acids, to selectively etch away certain atomic layers, leaving the 2D M-zene sheets behind. This method is crucial because it also determines what chemical groups are stuck to the surface of the M-zene, which really affects its properties. It just highlights that how you make it isn't just a detail. It fundamentally defines the material you end up with.
Right, the process is the product in a way. So, okay, we have this amazing toolkit now. Metals, semiconductors, insulators, all just atoms thick. The next logical step seems to be combining them. Our sources call this building with atomic Legos, making these van der Waals heterostructures. What does that let us do?
This is where things get really cool. Because those layers are held by those weak van der Waals forces we talked about. You don't have the same strict rules as in traditional chip making. You don't need the crystal lattices to match up perfectly.
Okay. Less constraints.
Way fewer constraints. It means you can pretty much stack any 2D material on top of any other, regardless of their structure. It opens up this almost infinite design space. You can literally design and build new materials with specific properties you want, layer by layer. Like stack a semiconductor TMD between insulating HBN layers, add some graphene contacts. Boom, you've built a high-performance transistor entirely from 2D materials. It's like an atomic scale construction kit.
Atomic Legos, yeah, that makes sense. And that idea led to something even crazier I read about, twistronics, where you don't just stack them, you twist them relative to each other by just a tiny angle, and everything changes.
Twistronics, that guy. Yeah. It's a genuinely new frontier. So if you take two 2D crystal layers and stack them with a very slight mismatch in their lattice size, or more controllably, you twist one layer slightly relative to the other, they form this larger repeating interference pattern. It's called a moire superlattice.
Okay.
This moire pattern acts like a whole new artificial landscape for the electrons moving through the material. And the most mind-blowing example is magic angle, twisted bilayer graphene. just by twisting two graphene sheets by a very specific tiny angle, about 1.1 degrees suddenly, completely unexpected quantum phenomena emerge, like unconventional superconductivity where electricity flows with zero resistance, just from a twist. This ability to basically engineer quantum states by controlling the twist angle. It's an incredibly powerful new knob to turn in material science.
It really makes you think, doesn't it? If a tiny twist does that, what other simple geometric things might unlock totally new physics? So, okay, pulling this all together, what does it mean for us? Where are we likely to see these materials actually show up? The sources mention several big areas.
Well, electronics is definitely a huge driver. Graphene, with those super fast electrons we talked about, ideal for high-frequency communications, think beyond 5G. For actual computing logic, though, the TMD semiconductors are probably more promising because they have that natural band gap, which means you can switch transistors fully on and off easily, high on-off ratios. Plus, they're thin, flexible, often transparent, perfect for new kinds of displays, wearable sensors, maybe even electronics woven into clothes. And in optoelectronics, things involving light, the way TMD monolayers interact really strongly with light, and the fact you can tune their band gaps. Makes them fantastic for super sensitive light detectors or highly efficient tiny LEDs.
Right, and I saw a mention of spintronics and valleytronics, using more than just the electrons charge.
Exactly. This is moving beyond current electronics. Spintronics uses the electron's intrinsic spin like a tiny magnet. Valleytronics uses another quantum property called the Valley index, related to where in the electronic structure the electron lives. TMDs are particularly good for this. The idea is you could potentially store or process information using spin or valley, which could lead to much faster computers that use way less power. It's a fundamental shift.
Okay, so electronics, optoelectronics, future computing. What about energy?
Huge potential there, too. That massive surface area we discussed makes them amazing electromaterials for batteries and supercapacitors, storing more energy, charging faster. MAZs, being metallic and having good surface chemistry, are looking particularly good for high-power energy storage, rapid charge discharge. They also show a lot of promise in solar cells absorbing light efficiently, and as catalysts, for example, helping to split water to produce clean hydrogen fuel. That's a really important one for the future energy mix.
Hydrogen fuel. Okay. Then there's the whole biomedical side. Biosensors, drug delivery, even cancer therapy, tissue building. How do these flat materials fit in there?
Well, that high surface sensitivity means their electrical properties can change dramatically if even a single molecule sticks to them. So perfect for making ultra-sensitive biosensors to detect disease markers much earlier than we can now. For drug delivery, you can load up their huge surface area with lots of drug molecules and potentially functionalize them to target specific cells, maybe reducing side effects. Some 2D materials like phosphorine and certain enzymes are really good at absorbing near-infrared light, which can actually pass through body tissue. So you could potentially use them for photothermal therapy, shine a light, they heat up, and destroy nearby cancer cells non-invasively.
Wow.
And yeah, tissue engineering too. Some are biocompatible and strong, so they can be used as scaffolds to guide how cells grow, helping to regenerate tissues or organs.
Okay, and one last area mentioned was advanced composites, making existing materials better.
That's right. Just mixing in even tiny amounts of graphene or HBN into polymers, like plastics, can make them significantly stronger, stiffer, and better at conducting heat. You could use enzymes or graphene to make plastics conductive, maybe for shielding sensitive electronics from interference or preventing static buildup. It's about boosting the performance of materials we already use or giving them totally new tricks.
Okay, so the potential is just staggering, really, across so many different fields. Which brings us to the big question. If they're so great, why isn't my phone made of graphene yet? Why aren't they everywhere? What are the biggest roadblocks to actually getting these materials out of the lab and into products? The sources seem pretty clear on the challenges.
Yeah, the number one issue, the one everyone grapples with, is what we can call the production dilemma. There's this stubborn inverse relationship between the quality of the material you get and how easily you can scale up production. The methods giving you perfect, pristine crystals like exfoliation, totally unscalable. The methods that can churn out large quantities like LPE or sometimes even CVD. Often the quality is lower, more defects, more variability between batches. So yeah, you could buy graphene powder by the ton now made by LPE, but is it good enough for high-end electronics? Often not. The quality control just isn't there yet for many applications.
Right, that classic engineering trade-off, perfect versus practical, quality versus quantity. What else is holding things back?
A really significant non-technical barrier is the almost complete lack of international standards. It sounds mundane, but it's huge. We don't have agreed upon definitions or standardized ways to measure and report the properties. If company A sells you graphene, how do you know what you're really getting? How do you compare it to company B's graphene? What's the flake size? How many layers? What's the purity? Without clear standards, it's incredibly hard for end users to trust the materials, design reliable products, or build a stable supply chain.
That makes sense. You need everyone speaking the same language. Okay, and then the big technical one, fitting these new materials into the way we already make things, especially silicon chips, the whole CMOS process.
That is a massive hurdle. Silicon CMOS technology is incredibly mature and optimized. Trying to slot in these new 2D materials is tough. Often, the high temperatures needed to grow good quality 2D materials via CVD, for instance, would just destroy the delicate transistors already built on a silicon chip.
No.
So usually you have to grow the 2D material somewhere else and then transfer it onto the chip. But that transfer process itself is tricky. It's easy to introduce wrinkles, tears, contamination, defects, all things that kill performance. Developing ways to grow them at lower temperatures directly on the chip, or finding much better damage-free transfer methods, that's absolutely crucial.
Okay, and finally, what about just lasting and being safe? If these things break down or turn out to be harmful, that's obviously a showstopper.
Exactly. Long-term stability is a real concern for some of the most interesting materials. Phosphorine, for example, reacts pretty quickly with air and moisture, so it needs really good protective layers and encapsulation just to survive. And as we think about producing these materials on a larger scale, we absolutely have to understand their environmental and health impacts. What happens when they get into the environment? Are they toxic? Do they break down safely? We urgently need thorough life cycle studies to make sure we're not solving one problem while creating a whole new set of them down the line. Safety first, especially for biomedical uses. So yeah, as we wrap up this deep dive, it's worth just stepping back and thinking about that huge shift, right? From thinking in 3D bulk materials to this world of 2D confinement. That extreme thinness, as we've seen, just rewrites the rules, changes properties fundamentally, and gives us this incredible zoo of materials to play with. But maybe just as important as the materials themselves is this idea that we can stack them like atomic Legos into these van der Waals heterostructures. And especially how that leads to completely new physics, like twistronics and that magic angle stuff. Yeah.
It's mind-bending.
It really is, and the potential is just huge, isn't it? Across electronics, energy, medicine, composites. But let's be realistic too. As you've heard, there are some serious hurdles before these things become mainstream. That production dilemma, getting high quality and high volume, the desperate need for standards so everyone's on the same page, the tricky problem of integrating with the silicon technology we already rely on, and making sure they're stable and safe in the long run. Those are big challenges.
Absolutely. And my kind of concluding thought on this whole field is that the future probably isn't about finding one single wonder material, the next silicone or the next steel. Instead, it's going to be about learning how to intelligently choose from this huge library of 2D materials and combine them, integrate them into complex systems that are engineered to solve very specific problems. It's about synergy between the layers. Really, it's about materials by design on an atomic level.
So here's something to maybe chew on after this. Given how fundamental these ideas are, quantum confinement changing everything, being able to stack and twist these atomic layers, what other seemingly impossible material tricks might be hiding just a twist angle away? Or maybe in combining dimensions in new ways. Thinking about those fundamental shifts, not just the cool applications, that's maybe where the real aha moments come from, the ones that could lead to the next big scientific leap. What else is waiting to be discovered in 2 dimensions?